Okay, what can you see
Looks
now?
good.
You can see the
Yeah,
slides?
looks good.
Yeah.
Mm-hmm.
All right, yeah, thank you. So actually, the title of my talk is Clothing Simple and Capturing Modeling Human Behavior in Large Scenes. It just, I got overexcited. I wanted to talk about too many things. And now preparing the slides, I realized, okay, I will just talk about Clothing Simple and I'll leave the capturing and modeling human behavior for some other time. Yeah, so basically this talk, I want to give a little bit of not only our most recent work, but a little bit of history of how the work we've been doing on modeling human bodies, and in particular in how to add clothing to these body models. So in terms of modeling people without clothing, I mean, you have seen throughout this this workshop tutorial that there's been significant progress. We're starting to have a very good understanding, very good models. And however, like, and this, you've seen that these models are realistic, they are easy to control and to animate. They had an impact already in many fields in academia and industry. However, like, those models typically do not have clothing, and adding clothing is still a major challenge. There's been like very exciting work, and not only the work I'm going to present, but also from different groups. And so we're making good progress, but there's still lots of open problems, and I'll try to point at these open problems. So we were interested in both problems. One is generation. So generation means you generate humans that look realistic and that you can control with a few parameters that are understandable by human users. And we're also interested in the perception and analysis. So this is given some pixels in an image. You want to understand what's going on. And yes, in Michael Black's group and other groups, we've been like kind of pushing towards getting a more and more detail, more out of the image. So not just restricting ourselves to detecting humans or detecting the key points, but really extracting the body shape and potentially clothing and the environment. You've seen the talk by CU, like there's a lot of work now, like in capturing humans also in context. And so I think this is very important, because if we want to build robots that are deployed in the real world, they have to understand everything that is going on, right? We cannot just limit ourselves to detecting like a few key points, because that's not how humans perceive the world. And you can imagine that these two problems are very intertwined, because if you have a good generative model, then you can address the perception problem better, because perception problem is ambiguous. You don't have typically the depth dimension, and there's occlusions and there's different illuminations. And so the scenes are difficult to interpret. All right. So basically today I'm going to focus on the works that we've done on modeling people in clothing. And I can easily divide the works into two categories. One is parametric mesh-based models. These are models that are built on top of the simple model, and they are mesh-based. This means like the model at the end of the day outputs a fixed set of vertices, and this has some advantages and some disadvantages. And then there's now recently there's been a trend of papers that generates implicit functions to represent surfaces. And this is in general like known as neural implicits. And we have work on general neural implicits for general scenes and objects and humans. And I'm not going to talk about those more generic works in this talk. I'm going to talk about this next Friday at 5 p.m. If you're interested, please join. This is a sharp workshop on 3D reconstruction, so also very relevant to this tutorial. And then there's like this, what I call hybrids, which are neural implicits plus simple or parametric mesh-based models. And you will see that these are trying to bring together ideas from models like simple and ideas from these modern implicit-based function models. All right, so let me start with parametric mesh-based models. So hopefully you've seen this equation now several times, you're familiar with it. So simple models, the pose-dependent and the shape-dependent deformations as a set of displacements that are added on top of um, an average mesh. So T mu is the average, and then you add like shape-dependent blend shapes, which are a function of some shape parameters, and then pose-dependent blend shapes that are a function of pose parameters. And so at the beginning, we're like, okay, how do we model clothing? So, okay, let's try the easiest thing, which is add a new set of displacements that is going to model the clothing. And this would go, for example, if you have the right displacements, you go from an undressed body to a dressed body. And using this very simple trick of adding a set of displacements, we presented at CVPR 18 what we call the video avatars. And I don't have time to explain in detail what video avatars are doing. But here I just want to focus on the representation. So for the purposes of this talk, you just have to understand that what we did is to take like a video of a person rotating in front of the camera, and we optimized the pose of the simple model, the shape of the simple model, and a set of displacements, D, which are a set of freeform variables, in order to maximize the overlap of the model here, the 3D world representation projected into the images. And so basically you minimize a distance between the rendering R of the model and the images, okay? And so we optimized, and the basic trick here is that you optimize one pose for every frame in the scene because the person changes the pose, but you only optimize one set of shape parameters and one set of displacement vectors because we assume that the clothing does not change as the person moves. And it's surprising how much you can get with just this simple displacement representation. You can get like different kinds of clothing, and it's relatively easy. Those are avatars that then you can be reanimated. You can change their shape because these are displacements that you add on top of simple. You can basically edit the results, right? So these are not just static reconstructions, they are also controllable models. I mean, now like the field has advanced a lot, but I think this was the first time that we demonstrated from just the video, you can get like this quality of avatars, including the hair and the clothing and so on. So we were already quite surprised, given that the representation is relatively simple. Yeah, the code is there, but yeah, unless this is not the state of the art anymore, so you would only use this code to compare, I would say. All right, so, but it had limitations because this was based on optimization, and we know that optimization is prone to local minima and it's low. And also the representation is simple and flexible, but it also has a lot of limitations. You cannot separate what is the clothing from what is the body. And for many applications, you actually need to do this. So like addressing the first problem, which is it's low and it's prone to local minima. What can we do to address this problem? So what we can do, instead of optimizing these parameters of the model, we can add a neural network front end that takes the input frames of the, oh, by the way, yes, good. Yes, so it takes the input frames and it predicts the output codes. And so basically what you have now is that you don't have an instance-specific optimization problem, but you're basically having a CNN that predicts those parameters. So you can optimize the CNN parameters, not from one single video, but from many different videos. And this idea of like this self-supervised learning, I mean, this was also presented for bodies without clothing. Like you probably know HMR. We also had a version which was called neural body fitting. And here we basically extended this idea to also predict clothing. So we have different works to doing this self-supervised framework. I'd be excited to talk about any of these works, but in this talk, I want to talk about the ICCB 19, which is called multi-garment net, which is the one that separates the clothing from the body and separates the clothing into parts. And I want to present this to pose a question later, whether this is a good idea or not. Yeah. So basically here, like the goal from the beginning was, okay, we have a source subject and we have a few images of this source subject, and we want to parse the body shape and the clothing garments, like the garments of the person, like separately, such that if we have a target person, like the guy here, we can map the clothing from the source subject to the target. Okay, so you can see that this guy now is wearing the same clothing as the guy in the source image. Now, to have this sort of control, you really need to separate what is the garments from what is the body. Okay, and this was the focus of this work. So obviously this displacement-based representation is not allowing to do this. So the first thing we needed to do is to actually also predict like a segmentation of the body into parts. And here we built on ClothCap, which we presented in SIGGRAPH 17. And so the idea of ClothCap is simple. Basically, the idea is that you non-rigidly register the clothing to the body so that you have a one-to-one correspondence between the body and the clothing. And once you have this one-to-one correspondence, you can do linear algebra with bodies and garments. Let me see if I can see the cursor. So here what you do is you take, let me see, it's including my screen, yes. Yeah, so you take basically the original garment and you subtract the body vertices that correspond to this garment, and you obtain a displacement D, okay? That now you can, you can take this displacement D that you computed here in the source, and you can apply it to a target shape, in this case, this guy over here, and you can apply this displacement that you computed from the source guy, and then you can apply it, and then you can basically cloth people by just applying a set of displacements. Very simple, but it's surprising how well this actually can work. And so here we did it for animating 4D scan sequences. So basically the real sequence here is on the left and the simulated one is on the right. So the right sequence, it's simulated because this person, which is myself, by the way, like it didn't have this clothing, right? This clothing was worn by Sergi. And yeah, I never wore this clothing. All right, so the thing is like, how can we do this more generically, right? So for any type of garment. So what we did is to register every single person for every single garment to a common template. And then we had all the clothing registered. And then we could basically do the tools, like use the tools we used for example, for building the simple model, but now for learning this model of garments and body. So basically what we do here is also this self-supervised framework in which you have the input images. We also get a representation that extracts some semantically meaningful information, like the segmentation of the person into parts. And then you have like network branches that predict each of the garment, which are now parametrized with a PCA model. I'm not going to get into the details, but the important thing is that you have networks that predict the vertices of each of the garments separately and the body shape as well. And then you basically compose these things using the same technique I showed for ClothCap, and you basically obtain the 3D avatars and you project them back to the image. And you evaluate the typical losses, which I'm not going to describe. You've probably seen this several times. And again, we showed that we can train this using 2D supervision and 3D supervision and combinations of both. Now, what is good about this is that now you have input images of a subject, and you have this network that predicts the garments separately, and you can apply these garments to any body shape. And so quite nicely, you can apply like the clothing of the source subject to you can predict it in 3D and then apply it to any body shape. These are good news. Now, what are the bad news? The bad news is that basically we have networks that predict the vertices of each of the garments separately, right? Well, there's two bad news, let me say. Like the first bad news is that this is quite difficult to register all the clothing garments to a common template. It's a difficult process. That's bad news number one. And bad news number two is that because we have networks that predict the vertices of the garment directly, we are not obtaining very detailed results. And that's because the input, which are the image pixels, are not very well related to the vertices of the model, right? The network has a hard time to figure out what's the connection between those two. So that's a problem. And let me see how I'm doing on time. Yeah. So there's a problem because there's a disconnect, right? And so what we've done in several papers is to use the UV transform, the UV map representation, in order to bring things more into correspondence. So the basic idea is to turn like a 3D reconstruction problem into an image translation problem. So what you're going to do is take an image. With a neural network, you're going to predict like this partial UV map, which you probably have seen in the tutorial in the morning. So basically, if you have a network that tells you for every pixel what is the corresponding body point, you can get a partial UV map. And once you have a partial UV map, you can predict the 3D shape by representing it with normals and 3D displacements. And so by using a simple image-to-image translation network, you can obtain like a 3D shape, including details, that is also controllable. And we've done also this to predict not only geometry, but also texture and so forth. And so these are the kinds of results that you can get. It's, I would say it's quite detailed, and you can apply it to any body pose. I'm going to show you also results for in the wild. And the nice thing is that, again, because these displacements are on top of simple, you can also basically reanimate these results. Now, I would say these are not as detailed as, for example, like works like PyFu. I'm going to cover this later. Yeah, I just want to mention that if you ever want to generate lots of different textures, we have this work at CVPR. All the code that I'm showing here and data is available in our website. So we had some work in which we're mapping shopping items, so with different textures, into the garments which are well registered with a simple model. So if you ever want to generate synthetic data or things like this, you can actually do this trick of using our work or our pre-computed results to just map texture from shopping items to 3D models. All right, so up to here, what are the take-home messages? So that if you encode the body separately from the clothing, then you can have control. You can map clothing from one body to another. It's also more difficult to do. You have to deal with the layering, you have to deal with intersections, and you have to deal with registering clothing. That makes things more complicated, but many applications require to have this sort of control. And yes, and then it's useful to have codes that carry meaning, right? That you can basically change, for example, like the size of the clothing or like who is wearing it and so on. And the other take-home message is that if you have a pixel-aligned prediction problem, like the neural networks will have a better time predicting details. All right, so these are models that I would say they are perception models because they go from images to like a 3D reconstruction. But sometimes we're also like the simple model, for example, like sometimes we're interested in producing to have a generative model. So to go from pose and shape parameters to an actual avatar that you can animate. So here, like this is work that we presented at CVPR last year, and this is called TaylorNet. And so what we were after here is to have a model that you can choose the shape of the person, you can choose the style of the garment, and you can also change the motion of the person. And this would produce like clothing that looks realistic on top of the simple model. Yeah, so basically the model allows you to change the style, it allows you to change the shape, and the model is trained on different garment categories, including skirts. So if you ever try to basically, what we did is we compiled lots of physics-based simulation and we try to learn this with a neural network. And if you ever try to do this, like what's going to happen is that everything will look smooth and it will not look very good. And so actually I'm not doing very well on time. So I think I will not explain a lot of details, but the basic idea is that you can have models that are specific to one style of garment, and those produce quite nice details. I was surprised by how much detail you can get with a simple MLP, We tried also more complex models, but with simple MLP already worked. The problem is when you combine different styles together, and I think the reason is that because different styles produce wrinkles at different places, then the network doesn't know what to do, and it basically smooths everything out. So the trick here is to have like a mixture model. So you have a low frequency prediction, and then you have, which you can separate the frequencies of a mesh using some geometry processing techniques. So basically you predict the low frequency first, and then you predict the high frequencies with a mixture model, making sure that these kernels that are the ones that tell you the contribution of each mixture, that they are very narrow, because if they are very wide, you're gonna average out again all the wrinkles. So this is basically the trick. And let me show you the results. So here we're changing the style of the person, of the garment, sorry. I warned you, I'm a bit tired. And you can basically keep the style fixed and change the body shape. And notice how the garment size does not change, but it basically adapts to the body. And the nice thing is that we train this with static poses, and it generalizes to basically animations. And this was actually, I was surprised. I was not expecting this to work as nicely. All right. So because I'm not doing very well on time, I'm going to speed up this. So I want to talk a little bit about implicit-based models. The basic the most important thing is that if you represent a surface, instead of using a mesh, if you represent it using an implicit function, you can track the changes in topology very well. So can someone tell me how much time I have left? Because I'm not sure if I started at 10 past.
You have like 6 minutes, I guess, 5-6 minutes.
About 6, but including questions or without including questions?
Yeah, I think including questions. The next talk is scheduled to start in 5.5 minutes. But
so I think then, like, I prefer to have questions. It's a pity because I couldn't talk about the other things, but I'll just jump to conclusions and I'll have questions. It's really a pity, but yeah. All right. So
so much cool stuff is coming by. Yeah.
Yeah, I mean, but I should have talked less. Basically, let me jump to the conclusions. Will be a little bit funny. So here, okay. So here are the conclusions.
By the way, Gerard, I also had to skip all my implicit stuff. I also was in exactly the same position. All the new exciting stuff has to.
Oh yeah. So, anyways, contact me if you want to know about the new stuff instead of the old stuff. All right. So basically, in my group, we are focusing on learning digital humans, and I hope you're convinced by this tutorial that we're making a lot of progress by capturing real people, and our focus is in modeling not only the appearance but also now we're also getting very interested in how can we generate behavior of humans in scenes. So basically, the take-home messages, which you will only partially understand because I only presented the first type of models, which are mesh-based. They are powerful and they are easy to use, but they are limited to one topology, and therefore it's hard to produce detail. And it's hard to produce different kinds of clothing, right? And neural implicits, they can produce many different topologies, and producing detail is easier, at least from images, but then having control is difficult. And but combinations of neural implicits and simple-like models can offer the best of both worlds. And these are the works that I couldn't present because I didn't have time, but they are coming, and they are offering like an opportunity to merge the good things of both models. Yes, and basically we need models that basically capture the variability of humans in shape, pose, clothing, texture, and now also motion within the environment. Thank you, and I'll be happy to answer 1 or 2 questions depending on how much time we have.
Then, hey Gerard, thanks for the great talk. I would like, given that you skipped the neural implicit stuff, I still would like to ask a question about this. Like, you're writing here that like combinations of this neural implicit functions and simple-like models, they offer like the best things of both worlds. what do you think? Is this like just a transitional technology where, like, as long as we have limited amount of data and maybe limited, I don't know, tools, that we now try to combine this, and then in the future, like implicit function will just take completely over? Or what is your guess, if you would need to make a guess, like within the next few years?
It really depends. So I think for clothing, I'm more and more convinced that they will take over because it's very flexible and you can represent many kinds of garments. So if you want to have a single model that can represent all, but for example, for undressed people, for things like, for example, clothing recommendation and things like this, you don't probably need to go through all the pain of doing an implicit representation, because there the shape, like the human body shape is quite well defined, right? And you can use a few vertices like the simple model to represent it. So it really will depend. And to represent like more general objects and so on, I think these implicit functions most likely will take over. But there's also an issue with the efficiency. Right now, they are still too slow. And that's why you don't see them. I mean, you still, like, most engines, they use meshes, right? And because they are much more efficient. So
I would guess that this maybe changes a little bit if hardware natively supports this.
Yes, that's also true. Yeah.
I think it's interesting how there's a parallel, though, in the implicit world to what's happened in the classical one, that you have a canonical pose, you model shape and, in that pose space, and then you model like pose-dependent deformations, from that. It sort of parallels what we've done in the mesh-based way.
But I have to say something.
I don't know. Yeah.
It is not always trivial to bring these ideas from classical world to the implicit world. And so this is a message, it's an implicit message to some like evaluators or reviewers, like that. I mean, this bringing these ideas from classical stuff to generalizing them to new representations for the implicit stuff is not always trivial, right? But yes, it's
so
cool.
We also have a couple of questions in the chat.
Okay.
So do you want me to read them? So which one do you think is more promising way to model garments? Creating a general model for all garments or creating separate models for each type of garment?
Oh, you're killing me. I mean, you can ask my students. I keep going back and forth with this. So if you choose a mesh-based representation, you will end up having to make one model per garment, okay? Because with one mesh, you're not gonna have, for example, like a dress that has two sleeves, like that has two, like, so basically, let me start again. So if you have a mesh-based representation, you cannot have one mesh that can represent all types of garments. Therefore, you have to resort to building one model per category. If you have an implicit-based representation, you can model like many garments into one, right? So let me show you just this quickly. Play from current slide. So this is what we call simplicit, and with a single model, we can represent different sort of topologies. So this is cool. You can do this kind of thing. You can transition from one garment to another, but you're losing something. You don't really have the correspondence between those garments. Well, maybe the correspondence is hard to get, right? But having the correspondence allows you to do other things, like, for example, edit the garment more easily, or mapping texture from one garment to another. So again, I don't have a more clear answer, because I see lots of advantages and disadvantages for both. So I would say like a one-for-all model is very flexible, but then you don't have these nice things of, for example, transferring texture.
Yeah, so let's see, that was super. I think we're now out of time officially, and it was great talk. It's exciting direction.
Yes, I mean, it was not a great talk because I talked only about the old stuff.
Well, it's a great area and it's exciting direction. So it was great to have you talk about it. The next talk is, no worries, it's great. The next talk is going to be super exciting because I've watched already, and it's what Microsoft is doing with Simple. It's pretty cool. And there's some cool clothing stuff that Gerard might like also. So it's pre-recorded, and so I'm going to play it.
Michael, so we have
oh,
like
you
a
want to do
big
an
one.
intro?
Yeah,
You want to do a
so
bio?